I love coming here. So much of life is about finding your people, and I spent a long time trying to figure out where my people were, and they're here.
So let's get started. A very good afternoon, and it's really good to see you all here. I'm John Haslam, and this is my co-presenter, Aditya Sarwade. And today we're going to talk about a memory profiling technology for C++ objects that we've created at Meta. So this technology is open sourced, and you can find it at objectintrospection.org and/or on GitHub. So we're going to try and take any questions. I know this is a big room and that can be a bit daunting for questions, so don't worry about it. But we'll try and take questions throughout the talk, but if we're running out of time, we may defer them till the end. So, but thanks in advance for your understanding on that. We're just going to see how it goes. Okay, welcome, come in. So I just want to start by stating what might be considered obvious for some people here, but it's really the key driving idea for this whole project. So, as Bjorn Strastrup states, types are the basic vocabulary of data, and it logically follows that objects built from these types are the common language of the developer. So in executing code, this basic vocabulary of types are instantiated into words and sentences that have meaning to the developer. And it's these sentences in turn that form whole stories, and it's these stories that are woven into the memory of our systems. But currently, it is extremely difficult, pretty much impossible, I'd say, to understand the state of objects in runtime memory, especially in production systems. And therefore, it's virtually impossible to know whether you've written beautiful poetry or a complete horror story. So that's as far as I'm going to stretch that analogy. So developers implement data structures, and they often have a mental picture of how these data structures will be populated in production. But however, even over time, or even immediately, these data structures come to be populated completely differently to how the developer thought. Now, this can happen for a limitless number of reasons. So the business you're in, hopefully this is it, the business you're in has been wildly successful, and you're processing much higher volume of transactions than you thought. Data models that you're ingesting are much larger than you predicted, maybe. Or maybe the compiler has thrown a curveball at you and has decided to subtly alter the way that your object is represented in memory. So consider this tiny, tiny little object. I mean, how could this go wrong? Yeah, it's 2 8-byte timestamps in a struct. Excuse the type defing. So later we'll consider how this definition, as part of a larger object in a sea of objects, wasted 10% of all the memory on a system. And we'll see how with object introspection, such a problem becomes extremely easy to identify and fix. See, by providing detailed insights into the runtime memory footprint of data structures, we can give developers and efficiency engineers high-quality data on where to focus their efficiency efforts. More efficient data structures can be implemented, and issues in data representation and requirements become really obvious. Overall, we can make more efficient use of what is a finite and often a scarce resource, and that's memory. Okay, so here is a trivial object definition. You're going to get used to looking at this throughout this talk. It's completely banal, really, isn't it? So just look at that a second. We will repeat it throughout the talk. So how do you tell how much memory this object occupies? Size of? Well, that's going to tell us the compile time static memory footprint, which isn't useful. For example, there's a representation of that. What about in a live application when bar objects containing strings are inserted into the vector? How do we accurately measure the memory footprint now, including all the dynamic allocations for the strings and the vector itself? Well, you could write your own code to iterate over those objects and measure their size. But this approach has major issues. It creates a significant maintenance burden on you, What happens when fields are added, removed, or renamed by other developers? The measurement code has to keep up with these changes. And while some container types are trivial to calculate their memory footprint, for example, std vector, other containers are much more complex to calculate their precise memory footprint, a std map, for example. You need to understand the implementation of each container to accurately measure their memory footprint. You have to manually write that measurement code for every object type you want to measure. And you, think about your code, have got a lot of object types. An instrumentation code like this is difficult to test properly, and that adds huge risk into, especially if you want to measure objects in production environments. So the reality is that most real-world objects are just too complex to manually write iteration and measurement code for. They have huge amounts of members with very complex types, and these members change frequently. Could you do this with a debugger, such as GDB? The question that gets asked, and it's a fair question. Well, you could possibly do something in the pretty printing Python interfaces. But again, you'd have to implement everything for yourself, and you'd suffer from the same problems I've just mentioned. And also, the runtime performance would be hideous. But I'll just leave that one with you a second. Today, we're going to introduce, as I've said, a new C++ object profiling technology that we've been developing at Meta for the last few years, object introspection, or OI. Aditya may refer to it as OI. I tend to call it OI, English, and I'll go, OI, like that. So think of it like that. This technology allows us to gain new views on the exact memory occupancy of arbitrarily complex C++ objects, arbitrarily complex. So with these new views of live objects, what we have consistently found within Meta is that even with objects that have been intensely optimized, there are virtually always optimizations to be made. So we'll take a brief look first at the goals of the project, as hopefully it helps understand the approach that we've taken. So as far as possible, we wanted to provide byte-accurate analysis of objects, regardless of their complexity and composition. We want to do that for every single member in the entire object hierarchy of a given object. And this means that we need to handle containers, and including your user-defined containers, and also all dynamic allocations. We need to work with regular production binaries in production environments. So this means that we need to work with optimized binaries running in environments which are often short on memory and under very heavy load. And we want to make it as easy as possible to capture these byte-accurate views of objects. So a developer's life is hard enough without fighting to make sure that an instrumented binary of yours is rolled out into production, and actually making sure you can get those results as well. So there should be no need to modify code or recompile a binary. And we also wanted to provide APIs that allow you as a developer to reason about the memory occupancy of objects from within your own code, so you can programmatically make decisions in your code. And we're going to spend the first roughly half of the talk looking at some pieces of the implementation, which I hope is not only technically interesting, but also allows you to understand better how to use this technology and how to better interpret the output that you're given. Now, first, I want to present a very high-level overview of what we're trying to achieve with OI and how we do that. So please, I know you're all absolutely brilliantly bright here, but please excuse a tiny bit of pre-comp sci 101. Yeah? Just to start with, going from top to bottom in that diagram. So you as a developer write your source code, and this is then compiled into object code or an executable by the compiler and the linker. Heard there's been a great linker talk. The compiler can also generate debug information, and this information describes numerous aspects of your application, including the composition of all your data structures. So OI uses this debug information to rebuild the objects with the same memory layout as that of your original source. Really important that. This includes putting every member with the right type at the correct offset. With the data structure rebuilt using this debug information, we can then auto-generate code to iterate over every member to capture its runtime memory occupancy. So this measurement code is then compiled, next stage, ready for measuring objects in live applications. So the object code is injected into running applications, and it can be invoked in one of two ways. You can use APIs to invoke it and consume the results directly from within your code. Or you can invoke this code on an object in a target process using a debugger-like approach, but we provide the debugger. So the sections for this talk are shown here, and we're going to start off by looking at the process of reconstructing objects. And for that, I'm going to hand you over to Aditya. Thanks, Aditya.
Thanks, John. So, to be able to reconstruct an object, we first need to understand the types of each of the object's members. Next, we need to understand the layout of the object and its members in memory. So this implies finding out the offsets of each of the members relative to the object's starting address. Furthermore, we need special handling for container types. For example, we don't want to reconstruct a vector from its base types. We are more interested in the elements that are contained in the vector. Each container has its own semantics and interfaces to iterate through the objects that are held in the container. So we have a pluggable framework to describe containers and how to process them. We won't describe that in this talk, but you just need to understand that any container, whether it's a standard container or a user-defined one, needs to be described in this way for object introspection to understand it. So first, we need to construct a graph, a type hierarchy of all the data members in all the objects under the root node. So the root node or the root type is the type of the object that we want to introspect. The terminal or leaf nodes in this hierarchy would typically be your primitive types, such as integers or floats. So to build this graph, we depend on compiler debug information. Compilers can emit debugging information, which describes in great detail many aspects of the application's behavior, including composition of data structures. The standard debug format on Linux and a lot of other Unix-like systems is DWARF, and this is the format that object introspection currently supports. We use the Dragon technology, which was developed at Meta, to parse debug information, and we are also adding LLDB support at the moment. Throughout this talk, we are going to use this example that is shown here. It's quite simple, but sufficient to demonstrate the concepts that we are talking about. Most objects which you would want to introspect may be much more complex than this. However, this simple type has enough to demonstrate how object introspection works with user-defined objects, containers, and primitive types. So the source code is first compiled into object code with debug information. Once it is compiled, OI does not have access to the source. To reconstruct this object, OI reads in the debug info of the binary and creates the type graph as depicted. The edges of the graph show the members of the object. In the type graph, you see the three first-level members of the object foo, members n, bar-vec, and foo-string. Importantly, the edges also contain information about the offset of each member, which is necessary to understand the layout of the object. Once we generate this type graph, we can reconstruct the foo type that the user wants to introspect. You can see that we have the two aggregate types, struct foo and bar as highlighted. The structures and primitives can be completely processed from the DWARF debug info, as it gives us everything to understand about how they are exactly laid out in memory. And finally, we have the container types. These are typically the most interesting, since they would contain dynamically allocated data, which is only known at runtime. Once we have the graph, we topologically sort the nodes to generate the types in the correct dependency order. In this case, for instance, bar has to be generated before foo. So we expand our simple example with some inheritance to demonstrate how that affects the graph. So foo inherits from my parent, which has 2 integers. OI generates the type graph for the type from the debug info as before. You see the my parent structure highlighted here in the type graph. Again, we rely on the debug info to know where in memory the members of the my parent object are relative to the base of the root object, foo. While reconstructing the object, we simply inline these fields into the struct foo itself. This is how we reconstruct objects with the exact memory layout of the original object. So now that we have done type reconstruction, let's look at how we generate the measurement code for the type that we are interested in profiling. So here we have the core generated code for the foo object. The more important bits for you to be aware of are highlighted in bold. Everything is driven down from a top-level getSizeType call for the root type. There are further calls to getSizeType for each member in the root type foo. We recurse through all the members in the type hierarchy this way. We have a getSizeType call for every unique type that we encounter. The purpose of each is simple: to record into a data buffer the pertinent memory occupancy attributes for the type in hand. Essentially, we do a depth-first search type of traversal through the type tree and log memory attributes of interest into a data buffer. Each getSizeType call appends to the data buffer according to a specific type. We have an internal type system based upon the simply typed lambda calculus. This allows us to ensure that the data written by the getSizeType function and the code which extracts the data from this data buffer match up. The rest of the code that you see here, that is the non-bold bits, are part of this typing system. Those are not particularly important for the purpose of today's talk, but they are important for our system to function. So let's focus on the barvec member, which is a vector of bar objects, as shown in the structure. Barvec is a type of standard vector. OI understands that this is a known container type and generates measurement code as shown. The attributes of interest in a vector are capacity and size. Furthermore, we again have a getSizeType method here, since we also want to recurse over every element in that vector. In this case, the elements in the vector are of type bar. The bar object, as highlighted here, contains just a string. So we simply call the getSizeType for the underlying string object. So I'm sure you're getting the picture by now. Standard string is again a known container type for OI. So we have predefined measurement code for it. For strings, we stash away into the data buffer the capacity and size of the string, and also whether short string optimization. Yes. Okay, so the question was who generates the getSizeType function? That is generated by OI. Yes, the tool we are discussing, object introspection. Yes. Yeah, so we basically first reconstruct all the types, and now that we have the type information, because we know each of the type, we start generating measurement code for it. Yeah. Okay, so yes, I was describing for strings, we store the capacity and size of the string, and also whether short string optimization is being used. Short string optimization is SSO. So most of you probably already know this, but SSO is an optimization where short strings are stored in line within the standard string to avoid a heap allocation. If the string grows beyond a certain size, It allocates memory for the characters dynamically. The SSO recording is done to accurately attribute the memory footprint to the string object. The whole of this generated code is then compiled using LLVM jitting libraries into platform-specific object code. And what happens to it then depends upon which route of measuring the objects we go down. So let's look at the first one, object introspection as a library. I'll hand it back to John.
Thanks, Aditya. Okay, so as Aditya's described, well, firstly, the following examples, important, were carried out with a simple piece of code which just adds a bar object to the barvec vector in a loop. I've got to apologize for some of the naming on the variables here. It's appalling, isn't it? But that's the hardest part of engineering sometimes. So we're adding bar objects to the barvec vector in a loop, and the string in the bar object is a random size, and that matters for the output that you're going to see. So the API to capture objects is ridiculously simple. So we've got, right, so this is it. Everything in bold is all you need to do to dynamically capture objects. Here we're capturing the memory footprint of the foo object that's passed into this function. There's a lot going off under the first call to set up and introspect. So it infers the type. It does a full code generation run by reading the DWARF, building the type graph, code generating into platform-specific object code, that's x86 here. And so that's as we've had described to us. But the first time this interface is called, we do all that. Subsequent calls, we don't do any of that. It's all cached. So once we've code generated for a type, we're done. So it's really fast then. So we capture a foo object. And the simplest thing we can do is throw it into our JSON exporter class, as shown here. We'll look at an example, and actually an example of what that looks like, what the JSON looks like. OK, so here's an example of the JSON output for a captured foo object that's had a number of strings inserted into the barvec vector. So the reconstructed foo object is on the right for reference. The static footprint is 80 bytes. And the exclusive size, which you can see is 4 bytes here, is the amount of memory attributed to the current object that doesn't belong to its children. So for an aggregate type, such as struct, that's padding. Next, we have the primitive types, which shown here, which are incredibly dull, but they are present, we can see them. But let's skip to the more interesting vector. There's much more going on. So the vector itself, at the time it was captured, here, occupies a mere 24 bytes, which is shown as its static size. But at the point of capture, it's housing 155 bar objects. And it's sized for 256, that's its capacity. The exclusive size of 3,256 bytes is how much of that capacity is not used by objects that it currently contains. So therefore, how much memory is attributed to the vector itself at the point of time of the object capture. The first bar entry in the vector, as we can see here, has a size of 32 bytes. But all of that belongs to the string object that it contains in its str member. And that can be seen. The string is 32 bytes static size with an internal buffer of 15 bytes, its capacity. Of these 15 bytes, there's only 12 being used to house the actual string in this object, and that's shown by the length field. And this shows us that for this particular string, we've no external allocation, and it's all short string optimization that's being used. So it's inline allocated. Okay. So the previous example showed us how the JSON output provided easy yet verbose display of an object. But let's just take a quick look at an example of how we can directly consume the data by a call to, the data returned by the call to set up and introspect when we measure an object. So the measurement code is executed, and the results are written into a data buffer. The contents of the buffer are made accessible to us via an iterator that's returned from setup and introspect. And as we can see here, highlighted in red, that's an introspection result object. So the results are presented as a sequence of element objects, where each element represents a data member, such as an integer, a string, a vector, for example. And the order they're presented are the order in which they were encountered as we iterated the object when it was processed by the measured code, the measurement code. We simply iterate through each one and extract the relevant pieces of information that we need about that element. So we start at the top level element, which represents the foo object. Then, as we go through the elements, we pass through the boring integers and we get to the vector of bar objects. The first element would be for the vector itself. Then for each item in there, in the bar vector, you have two elements in this case. You would have an element for the bar object, and you have an element for the string object that it contains. So what you would have in a vector is a sequence of bar, string, and then that would carry on until we've exhausted that vector, and we would come to the top level string object, the foostra, and that would be in the last element. It's really simple. So here's a simple example, I think it's simple, of how you would find all string objects in an object that you passed in. Just look at the code a second. Most of it's actually printing. So all we're saying, I mean, firstly, I think this is ridiculously simple. Yeah, that how do you locate without knowing the structure of an object or anything about it? That's all you need to do to locate all stud string objects within the entire object hierarchy. So the only thing that probably needs calling out here, just for your understanding, we haven't sort of shown what's in the element object, but it's that the type names member, which is referenced in this code, it's an element in the, it's a member in the element, and it's just a vector of type defs, or the actual base type name that a type is known by. So all we're doing here is going through all elements, looking for stud string in the types. And if we find it, we've got a string in our hand. And then we just print the name, the length, and the capacity of that string. We see in the output on the right that we have 6 string objects coming from bar objects, the str name, and a foostra object, which is in the top level foo object. And as you can see, it's empty. There's nothing in it. It's that simple, really. It's all you have to do. So now, that was a very high-level overview as how you can introspect and consume results from the library interface. We're going to look at the profiler interface of object introspection. So the object introspection debugger, or OID as we call it, OID, is a traditional Unix debugger-style application where a tracer acts on a traced application, and that's the tracee in Unix polons. And the high-level aim of the OID debugger is to make a thread in the target process execute the measurement code to capture a particular object at a particular point in the thread's execution. That will become hopefully very clear what we mean in a minute. So we'll look at how it achieves that. So a high-level overview of a few of the key areas of the OID debugger. So it does the type reconstruction, code generation, and compilation, as we've already had described. The measurement code produced by the code generation phase is injected into the target process. Now, running processes don't have any memory where you can just place code. It's all been constructed before. So the OID debugger creates a text segment in advance where it's going to place that code. It also creates data segments where it's going to house the results of the measurement code. Now, just regarding thread management, so threads in a target process need to be manipulated. Register sets need to be changed. We need to capture threads and make them do things. So we use the ptrace interfaces. They're a long-standing Unix interface, been around since 1970. And we only stop individual threads. That's a key thing. People always say, oh, we stop everything. Only ever stop individual threads. We never stop all threads. And internally within Meta, we work with very active processes that have thousands or tens of thousands of threads sometimes. And we use standard techniques for a debugger to capture running threads. And this is dynamically inserting breakpoint traps at specific areas in code, instruction rewriting. So we'll look at slightly how we do that. And OID also reaps measurement data when the target process and the objects have been measured and processed. And we just process that, reap it and process it when we want to, actually. So bear in mind, this process is all hands-off. It's not like GDB Interactive. It's completely hands-off, driven by a small config file. So let's look at how you'd invoke the OID debugger called OID to capture an object using this example, literally called example function here, which takes a foo object. Think about your code and the kind of objects and function names you're dealing with. And it returns a bar object. So looking at the OID invocation at the bottom of the screen, the bottom of the slide, going from left to right, the minus JSON specifies that OID should generate JSON. The minus PID specifies which process to attach to. This is just a simple test program I had running. The minus capital S specifies the object we are going to capture and where in the code we're doing it. So let's see what's happening here. So the colon delimited tuple has 3 components which tell us what we're going to measure, where we're going to do it. The first one says that on entry to the example function, we'll capture the object that is passed as its first argument. And we can see this is a foo object. And we're using mangled symbol names here, so that's why they look a bit strange. And we index from 0. So the first arg0 is the first argument. The second example says that on return from the example function, we capture the object that was passed in its first argument. The third example here says that on return from the example function, we capture the object that is returned from the function. And in this case, it's a bar object. So we capture a bar object when it's returned. We can also introspect multiple arguments at once. So here on return from the doIt function, we capture the first and second arguments, which are foo objects. It's a bit awful to look at that mangled version. And additionally, we can introspect that this pointer, this is a very powerful thing that we do an awful lot within Meta. So we can introspect that this pointer on entry or return from a class's member function. So here we capture the foo object on entry to its destructor. There are issues with inlining, which I'll mention at the end of the talk. And, So we can also capture objects that are defined as globals, and here's how we would capture the global object named myGlobalState. Okay, I'm going to briefly look at the flow of execution of how we would actually capture a foo object when a thread calls the example function in a target process. So the measurement object code is copied into the target process into a text segment that was created by OID. So OID also creates a separate data segment, as we previously mentioned. And when OID is ready to actually capture an object, we replace an instruction in the function prologue. Remember, this is an entry, on entry to the function. We replace an instruction in the function prologue of the example function. And we replace it with a breakpoint trap, which is a standard mechanism used by debuggers to gain control of threads in a target process. So this, at the minute, is x86, so it's an int3 instruction. The next thread, to call into the execute function, will execute the breakpoint trap. And that thread traps into the kernel, which then notifies OID of this event. OID then locates the address of the object being measured in the target process and sets up the registers of the target thread in order for it to be redirected to execute the measurement code. Wow, animation crazy. Thanks, Thierry. So the redirected thread executes the measurement code, which populates the data buffer with all the memory occupancy information of the object being measured. And at the end of the code sequence, there's another breakpoint trap. So execution of that trap leads the control being transferred to OID for that thread. And so OID then does some ancillary tasks and sets the thread's register state up accordingly so that it can resume execution from where it was originally executed, in the original call site. So OID removes the breakpoint trap, and the thread is continued, and it carries on executing as if nothing had happened. Yep. So OID, when it wants to, just some point asynchronously, copies the captured data out of the target process and processes it. And there we go. So this data is populated into a RocksDB database from where it can be post-processed. So you've already seen the JSON formatter, but it's actually trivial to populate your own database with everything that's in there. This is a slight tangent, but one that's really, really important. It's an interesting one, I think. So we found that processing large amounts of debug data, some of our binaries have 10 to 15 gigabytes of debug data, at runtime uses considerable amounts of memory, I/O, and CPU. We therefore introduced the ability to generate all this measurement code to do all that process offline, asynchronously, whenever you want. And this means that when you want to introspect a given type, an object, you don't need debug information on the production system. You also don't need to use production resources to actually process it. Generate the binary. So we basically went from taking 15 minutes, some of these big complex objects with lots of debug data, it took 15 minutes really to generate the object code. We went from there to 1 second to do the whole process, because the object code is ready, just measure the object and go. So that's the thing we call caching. It's available in our open source repo for you to use. Really important to use. Okay, so that was object introspection as a profiler. Now we're actually going to look at some use cases and what we've done with it. I'll hand over to Aditya.
Okay, thanks, John. So I know that was a lot of implementation information about how the tool works, but to really get an idea of why the data captured by OI is extremely powerful, let's look at some cases where we applied this tool to make memory improvements to our services. So for containers, this is the first example. For containers such as vectors, you have two attributes, capacity and size. So capacity tells you how many elements this vector has allocated memory for. Size tells you the actual number of elements in the vector. Since capacity is always greater than or equal to size, some of the memory may go unused. For a given container instance, this is how you would calculate the amount of memory being unused. That is, capacity minus size multiplied by the size of the element in the vector. So for one of our services, we captured 2,800 instances of a complex object. This structure had highly nested members and had hundreds of fields. The service was loading hundreds of thousands of instances of this object in memory. The type names are anonymized, and we will call the introspected object foobar. So all the members of the foobar object were grouped by their type path after they were captured, type path being the path in the type hierarchy. We then sorted the members of the object by unused size. This object member feature showed up at the top. So bear with me, let's quickly take a look at the columns. The type name of this member is a fully small vector, which is a known container type for object introspection. Small vector operates similar to the short string optimization for standard strings that we saw earlier. It stores up to the specified number of elements in line within the container. If the container size grows beyond that, it does heap allocations. In this case, the small vector contains elements of type X and can store up to 10 elements in line. The next column number is the number of times this field was encountered. So in our sample of 2,800 foobar objects that we captured, this small vector appears over 400,000 times. That is about 150 times per foobar instance. The element static size is the size of the element in the container. In this case, it is the size of type X, and it is 8 bytes. The length column is the average number of elements in the small vector across all the 400,000 instances. The length here is really the size property of the container. So on average, this field has 2.3 elements per instance of the small vector. The capacity tells the average capacity of the small vector, and that is 10 elements. The next two columns, the dynamic size, are dynamic size and total size. The dynamic size is the average dynamically allocated memory by this small vector. Since it is 0, that means all instances of this small vector stored the elements in line. Total size is the average total size of the small vector, including static and dynamic size, across all the 400,000 instances that were captured. The final column, cumulative unused size, is calculated as described by the earlier formula. Capacity, that is 10, minus size, 2.3, multiplied by 8, that is the size of element x, multiplied by the number of instances of the small vector, that is 400k. So this is the cumulative amount of unused size by this small vector across all our samples. Now you wouldn't think that is a lot of unused space. It is just around 25 megs. However, we have only sampled 2,800 objects, while the service loaded hundreds of thousands of these objects. So we can probably do a better job of picking the inline size for the small vector. Because OI captured details about every single instance, we use it to plot the distribution of the number of elements in the small vector. Over 90% of the time, it contains less than 4 elements. We ran some experiments to figure out the correct inline size to set for the small vector. We could set the inline size to 4, but that started eating into the memory we could potentially save by making this change. We could set the inline size to be smaller than 3, but that introduced CPU regressions, since it resulted in extra cycles spent in heap allocating the data in many cases. This service was quite sensitive to CPU regressions. A size of 3 was the sweet spot, which showed no noticeable CPU regressions, and ended up reducing memory used by these objects by 1.5 gig in the service. We have made many other similar improvements in some of our largest services. For instance, removing containers which are never populated, or replacing containers with more memory-efficient counterparts. For example, replacing vector with a small vector, if it has small number of elements, or replacing standard map with more memory-efficient Folly containers. Let's take a look at another example, and this one is slightly different from the memory savings we had normally done before. One of the services we were profiling was memory bound and was frequently running out of memory. This service loads a lot of foobar type of objects in memory. This foobar type is different from the previous example, just to be clear. I hope that stack is visible to everyone, but I'll highlight the important parts. So we introspected 1,000 objects of this type and generated an icicle view from the captured data. As we can see, this is a reasonably complex object that has around 7 to 8 levels of nested types. At the top in this graph, you have the foobar object, and below that is the breakdown of each of the members of the object by memory. Take a look at this highlighted array of timestamps in the graph. This highlighted piece of memory can't be attributed to any member in the parent timestamp structure. That is because those are padding bits added in by the compiler. We looked at the structure which object introspection regenerated using type reconstruction, and it looked something like this. This structure is 8-byte aligned, and those two booleans added at the end cause 6 bytes of padding to be added by the compiler. Normally, this may not be an issue, but there were many instances of this object loaded in memory. Now, you might wonder why the object is structured this way. So we looked at the source code for that object. Turns out this was a thrift object. Thrift is the serialization and RPC library that is used at Meta, similar to Google's protobuf. This is the same example that we talked about in the introduction. This looks like an innocuous structure from the source code, and it is not straightforward to detect the resulting inefficiency unless you know exactly where to look. When Thrift generates the C++ structures from this definition, it implicitly adds those two booleans as metadata to indicate whether these two int64 members are populated or not. In this case, these fields were always populated, so the isSet bits were not necessary. We added thrift annotation to the structure to remove the isSet bits. And after making the changes, we profiled these objects again. As you can see, the wasted space under the timestamps is now gone. This change reduced the P95 memory usage of this service by 10%. So hopefully these two examples, they demonstrate why having such fine-grained observability into your objects is extremely powerful. Having access to such views enables developers to make more memory-efficient decisions about their code. Most of the memory improvements we have made were realized with very straightforward code changes. In addition, with things like continuous monitoring of their objects, developers can also prevent unintended creep of memory regressions being introduced in their systems. They can also make precise attributions of which changes caused the regressions in the first place. So yeah, with that, I'll hand over to John to finish off.
Slightly off script, but just to iterate that this is a really important thing that Aditya mentioned at the end. Within Meta, regressions really are very important, especially around this kind of work where you don't know you're putting these regressions into the memory of your systems. And so you can capture objects constantly, and that's the whole thing. You can capture them so cheaply, and we can just measure them constantly and get views day by day, hour by hour, actually, of how the objects are mutating over time. And so, yeah, I think it's a really important point here. So we're coming up to towards the end, but I just want to point out that as with all technologies, all is not perfect in the landscape. And so I want to draw your attentions to a few things that you may need to be aware of if you want to apply object introspection to your code, which I hope you might. It's Linux, DWARF, and 64-bit x86 only at the minute. And we would gladly work with contributors looking at implementing for different hardware or debug information types. Also, dynamic linking. So object introspection has been deployed within Meta, and that's the environment where it's been tested and exercised. All the objects, pretty much, and code sites of interest that we work with come from statically linked executables, because that's the mode that we extensively use within Meta. Dynamic linking hasn't been tested well, and therefore you may have issues. It's something that's on our list to complete and do more testing. Debug binary is the same thing. And strange as this sounds, we actually work almost exclusively with optimized binaries. So binaries that have been generated with low optimization levels, so minus 0.0 particularly, you may have issues. You may not, so but it's on our to-do list to actually test more. Inlining functions, I mentioned this in the talk. Inlining actually presents a number of technical challenges, which we're kind of halfway through. But for this is just for the OI debugger, and we're not fully on top of them yet. So the bottom line currently is that we can't work with functions that have been inlined. And data races, another important one. Iterating over objects while those objects are being modified by other threads, not actually a problem for the OI debugger. As it's a ptrace consumer, the kernel will notify it about any signals that the target thread generates. And therefore, if a pointer is modified while the target thread is executing measurement code, the resulting signal, which most likely is going to be a segmentation violation, a segv, that will just be delivered to the OI debugger on behalf of the target. And then we get a choice to do what we want with that. We simply abort the current measurement code execution, and we just put the target thread back to where it was executing from originally, and it just carries on as if nothing's happened. You just don't get any introspection results for that run. This is not the case for object introspection as a library, because you're executing in your code without any protection. So you just need, as a developer, need to ensure that concurrent modification isn't possible, same as you would normally if you've got multiple threads modifying data. That's up to you as a developer. And user-defined containers, we do work with them, but first you have to describe them. So if you've got your own user-defined containers, which you will do, you have to describe them in a particular format. And to start with, you're probably going to need to come to us, and we will happily work with you to do that. The format's not too bad. but you're going to have to implement a few things. Template specialization of containers. So if the application specializes some containers to behave differently for a certain type, we can't deal with that. So, for example, a std vector of balls, that is a template specialization, but we do deal with that because that's in the standard. But if you do that yourself, we can't deal with that. Virtual inheritance, the memory layout of object is only known at runtime. This is a problem for us. Since the measurement code we generate relies on knowing the offsets of each member in your object. And this makes it challenging to figure out the memory layout of objects from debug data, since the layout of that object is only decided at runtime. So at the moment, we can't introspect objects which do virtual inheritance. C-style unions, not generally an issue for most C++ developers, but we can never have enough information from the debug data about at runtime what type is actually held in that union. We can't deal with them. And lastly, pointers and void stars. Well, we can't really be sure what's at the end of a raw pointer. So by default, we don't follow them. You can choose to follow them through a configuration setting if you know that there's going to be valid memory hanging off those pointers. We absolutely have no idea what's at the end of a void star, so game over, we just ignore them. Okay. Now, I know that's been a whistle-stop tour of object introspection. I hope you've got something out of that. So we've come to the end of our talk. Now, I would say that the whole development team are here, sitting in the front row, and they do a lot of the smart stuff on this. And we'd love to talk to anyone who has questions or would like to just chat further about how we've done things and what you can do with your code. So you can also find us at objectintrospection.org, and that will actually get through to our GitHub repo. It's a Facebook experimental repo, Object Introspection. But I really hope in the end that it provides as much value to you as it has done for us, and that's been enormous. So thank you, and we will take questions. Yes.
Hi. So first of all, this is amazing. I think it's a space where there's a lot of work to be done. I think memory troubleshooting, I think it's a big open topic. So I have actually two questions. One question is, typically when I go for chasing a memory leak or trying to understand something, I need to look at something top down, right? I have a process that's leaking. I have no idea where to look or anything. So kind of what are your thoughts on this kind of catch-22? Kind of where do you start?
Yeah. I mean, do you want to answer that because you're better at heap profiling?
Sure. So it's generally the service owners have a better idea of which objects might be a problem in their services. What we have typically done is either rely on service owners to give us pointers on which objects to look at, or we rely on heap profiles, basically. So whichever object typically shows up taking a lot of space, but heap profiles are not very granular. So you just know that there's some object which is taking up too much space. You don't know where the exact attribution within your data structure. So that's typically how we go about it.
Yeah, we'd go through execution stacks in the heap profile and look at what allocations are being done in them, then go and grab those objects.
Okay. And the second question is on the, you said basically if you have a custom container, you have to provide the code for it. So I guess the question is, what makes the difference between a container and any other object, right? If I have my own object that happens to have a primitive array, is that a container already, or kind of what's the general?
Yeah, I think that's a very good question. Whether you want to add your type as a container to object introspection really depends on the implementation of the container. So if you have a container, for instance, say a vector-like container, where you just have a raw pointer to some piece of memory, and you store tertiary data like the length of the vector separately, object introspection is not going to know how long that, how many members are in that element, unless it knows it has to look at the length as well. So if your object defines all the elements which are properly typed, you may not even have to add it as a container to object introspection. I don't know if that makes sense.
Okay, so technically anything that has a pointer probably needs to have some.
Yeah.
Absolutely.
I think that's probably kind of the.
Yeah, I mean, for example, take a standard pair. A pair just has 2 elements, so there is no need to add it as a container. to object introspection. It's just going to boil down to 2 elements that show.
Okay, cool. Thank you.
Yeah. Okay, thanks. Yes. Oh, sorry. Oh, yes.
Hi, yes, hi.
Hey.
So my question is about adoption. So this is a tool, awesome tool that your team built. And I imagine early on you went in with a lot of major services and worked with them to do this memory profiling. So what happens next? Like how are you advertising this tool? How are you making teams aware on how to use it? Like, is this something that's going to be enabled by default?
You work within Meta?
I do work at Meta, yeah.
Oh, I'll speak to you after then. No, but yes, we've generally done the driving ourselves of going to services and just, because, developers, they're busy, and we just say to them, hey, which objects are of interest to you that are major in your service? Or we go and look at heap profiles ourselves. Adoption and how we've been very busy implementing. There's a lot of technology in this stack. So I think, unless you want to say something, Aditya, it's something that we've driven ourselves, the adoption. And when developers get hold of it, they're like, oh my goodness, and then they use it themselves. But probably need to speak to you though. Yeah.
I'll speak to you after.
Yeah, please. Thank you. Oh, we've got more. Yes.
I was wondering how the tool reports statistics if I allocate myself a memory to construct an object. So if I allocate, say, a buffer over here, it's 100 bytes. And I create this object, I know it's 100 bytes, and I say, please create it using that thing. Is it going to report that both those things are 100 bytes? Is it going to tell me something?
Sorry, could you repeat the question?
Are they separate allocations, or are you actually just, you got pointed to the same?
This is just an array of 100 bytes. That's it's a blob over here.
Yeah.
And I'm saying, okay, construct another object, but don't allocate memory, use this thing to use as. So I was wondering what it's reporting.
Oh, so at the moment we have capabilities where we detect whether a piece of memory has already been encountered based on the pointer. And if so, we we make sure that we don't double count it. You could get into funny situations where if you hold pointer to the middle of the memory somewhere, I don't know if you deal with that yet.
We are open to problems like that.
Yeah.
But
but as long as both the pointers are pointing to the same piece of memory, we will make sure that it's not double counted.
Okay, thanks.
Yeah. Yes.
Thanks for the talk. Just curious, can OI do object serialization at all?
So can it
do serialization, sort of like boost serialization, or basically?
Are you thinking of for capturing objects?
Yeah, for saving and then maybe restoring objects later.
Okay, I'll answer that. Yeah. Yes, it can, but no, it can't. As in, obviously, that has issues around capturing data, and we are very conscious of what data is being captured on our systems. So we did implement that, just to be very open and honest. We're being filmed over here. As in, we've implemented it, works very well. We haven't actually put that into the technology because, there are concerns around you just go randomly capturing objects. We need to make sure it's got no user data in there. But if you can make sure that it's got no user data in there, then we would like to do that, and it's a great use of the technology. Yeah. So it's not hard to do.
Thank you.
Yes. Sorry, yeah.
So my first question is, when you're trying to regenerate the code, I don't know much about DWARF. So do you have access to private members, and are you able to regenerate the codes for that?
Yeah. Yes. Well, yes, we regenerate everything publicly. Because we regenerate, we rebuild a new view of the object. Okay, so anything private gets made public.
Okay. So at least you have access to that.
Yes.
So you can do that. Okay.
Yeah.
Second question is we use templates very heavily in our code. So when you mentioned that in your limitations, is it something like a no-go at all? Like, for example, if I have a template class, objects of template class, am I able to introspect them, or it's not possible at all? If it's not, then what is the real problem behind it?
No, so we do work with templated classes. What we don't work with is if you template specialize containers for a specific type. For example, so if you have a foo type, and in your code, if you modify standard vector to behave differently for a type foo, that we cannot do.
Okay.
Yeah, we deal with a huge amount of templatization. Obviously, our code's heavily templated.
Thank you.
Thank you. Yes.
Hey, thanks a lot. So 2 questions regarding the profiler use case. So first of all, the thread or basically that hits the breakpoint and then does a traversal.
Yeah.
Does it encode JSONs or it has
no, that's all? Yeah, sorry if I wasn't clear on that. Yeah, no, it just literally rips through the code and dumps out the data into a text segment, just iterates over the members, and then OID does that lazily. All that's done in OID, it's just read out and processed, reconstructed into the object shape, and then that's all done offline. We try and keep it as fast as possible in the measurement code.
Yeah, that's actually like a challenge because we kind of write serialized data to the data buffer.
Yeah.
We have to deserialize it properly in the object introspection.
A lot going off in there.
Yeah. Okay, thanks. And secondly, so the specification string, if I understand correctly, describes when the breakpoint should be set and which argument or which variable to specialize. Maybe there could be value to allow adding some more context, like having another variable as an extra identifier, a part of the type, so that you can.
Indeed. Yeah. There's lots of stuff that can be. I'm being reminded our session is actually over. I thank you very much. I will happily, please, anyone who's got questions, come and ask us. The rest of the team are here. And thank you again for attending. I've enjoyed it. I hope you've enjoyed it remotely as much as I have. So thank you.